Okay, so right now what we're going to do is we're going to do a self DC shunt generator. So here's quite the drawing, I know. This one here is now going to tell me my load amperage. This one here is going to tell me my field current, and I want you to guess what the armature amps are going to be when I get to full load. Remember, armature amps is I load plus IF. Up here I got a voltmeter across the shunt again to show you in a self the terminal voltage is equal to the shunt voltage because it's a parallel circuit. So ET there is the same as up there when you do math. I might just, well, we'll let you guess that ammeter. So right now, if I go over here, there's the green thing, the rheostat. That changes my magnetic field, no? So right now, my voltage there is about 17 volts. My voltage across the shunt is roughly about 7 volts. A little bit difference there at no output voltage. But basically I got a high resistance up in my shunt field. So therefore I'm going to have a low magnetic field induced into the armature, and therefore a low output voltage. It's pretty much directly related to current through the shunt field. Now I'm right here and I'm going to decrease my resistance in the shunt field, and now my voltmeter has built up to 136 and this one is built up to 136. So that's when you can basically safe to assume for any math that ET down there is the voltage applied to that shunt, because they should be equal. But as I shown you, I have a very high resistance within the shunt field. There's a little bit difference between the voltages. So you will notice too that as I change this, I'm changing the current through the field. So I'm just going to get that up to full output. I'm about 136. You'll notice basically in my other one, the separate excited, I was about 138 at my full output voltage. But here's a little bit different. So when I start adding load, I start having current flow through the load. And I also drop my output voltage. So right now my terminal voltage is about 104. That also directly drops my field voltage, which we'll call terminal voltage. So you'll notice here now when I take off load and my voltage goes back up across that shunt field, doesn't my current go back up? So it's directly connected. So as I add more load and there's more current in the circuit, there's basically less output voltage. So essentially what's going on here is at full load I have about, let's say, I can't read a scale, but yeah, that'd be about maybe 7.5 amps, 7.6 amps through the load. Up here I have about maybe 0.78 amps up there. So coming around, when then I just add up my two currents, because isn't it flowing from our A2 to A1? So my armature amps would just add up. When I know my armature amps and I know the resistance of that armature, I can calculate my voltage drop, add it to my terminal voltage. Now I know what we call our generated voltage. So not too much to see here, I guess. You'll notice though, I don't have anything directly connected to this bus voltage anymore. It's simply just feeding off its own armature. So when I go down here, you'll see F2. F2 is now just connected over to A1. This goes off to the voltmeter if you're wondering. This here also goes off to the voltmeter. And this is F1 coming back from the rheostat and the ammeter. and A2 is just fed off to the rheostat. So we're generating a nice supply DC voltage there. So that is our demonstration of a self DC shunt generator. So unlike the other one, when I reverse the current flow through my shunt field rheostat, I basically change my output polarity. So I'm going to do that for you here. You'll see I have 96 volts at my terminal. Right now I'm going to take these out and connect them there. It basically is destroying that residual magnetism right now in the frame. You'll see keeps breaking it down and down and down, but it won't reverse voltage, it won't reverse current flow, unlike the separate. Okay, so I don't know, I might have actually just broke down the residual magnetism in this frame, but we'll change it back and see if it'll build up voltage again. Oh, I didn't destroy it enough. Oh, maybe I did. We'll see here. If it gets over 10 volts, we're good. Yep. And now it's basically realigning those domains. Oh, there's our lights. So yeah, so we're back up to our nice running voltage. So those are some of the things you can't do. So if, for instance, my prime mover ever went backwards in this circuit, I would need to maintain F1 positive. F1 always needs to be positive. And that is kind of our what ifs for this circuit. If, for instance, in a generator, my field circuit became very high resistance, I lost my output voltage across that circuit. I also directly lost my output voltage at the load. There's a little bit of residual magnetism, but nothing much. So then when I go to plug this back in, I'm getting my voltage. It's building back up here. It's building back up there, and there goes my light. No? And now current flow is restored to the load and to the field. So that is pretty much self DC shunt generator in a nutshell of what to do. One other thing I could do is reverse my prime mover. So since I'm here, I'm going to demonstrate this to you. Just like how I reverse current flow through that field winding, I'm going to reverse our actual prime mover. You'll notice it's telling me a negative polarity now, because essentially I'm going counterclockwise and A2 is in reverse direction. So now in the drawing you just simply flip A1 and A2 always. So A2 should be on this side more negative, and A1 should be on that side because A1 is now more positive. But you'll notice it won't build up voltage. So before I destroy all the residual magnetism in the frame, I'm going to reverse these leads again. That was a takeoff sound, right? So we'll count to 10 there. Oh, there we're on. We're up and running. I don't know. Is it going to build up voltage this time? It's slowly getting the magnetic circuit back, but you know what? I think that was too much for it. It's not going to build up the voltage. This is just the residual magnetism in the frame, but there's not enough domains in that magnetic material to be inducing more voltage. So what I'm going to do is shut this down. And I'm going to take our DC voltage here, take off our F1 and F2, take the positive lead. I've disconnected essentially the whole upper half. We're back to a self-excited type scenario. So now I'm just going to take this whole 120 volts DC and inject it right into F1 and F2. So I made F1 positive in reference to F2 being negative. I may have to sit here for about 4 minutes, you know, to make sure it's really good, but this is the best way we can do it. So once I flashed the field and restored my magnetism to F1 positive and F2 negative, the machine will just basically go back to operating as normal and build up voltage. I'll see if maybe right now we got it. So that was a spark, right? Because you always shut stuff off, but this is a trained lab environment. So I'm going to put my generator back together. I'm going to take this voltage over into here. Okay, so you see now that I flashed the field, I basically got magnetism building back up. So make sure you have that control set at minimum resistance too when you're starting it up. Otherwise it might not build up voltage. So I'm pretty much back to operating as 103 roughly. And the world is good on this DC generator, so one thing that could happen is, I'm just going to throw it at you, not that it's too important. I'm going to slow down my prime mover. Doesn't slowing down my prime mover also slow down my generated voltage? Right? So if this went even slower, it would generate less output voltage. If I go faster, I can generate more output voltage, no? So essentially what that comes down to is that other math question where it's just a simple ratio, no? It's voltage 1 over RPM 1 is equal to voltage 2 over RPM 2. So if I wanted to know this and I knew this, this, and this, cross multiply, right? I get RPM 1 times V2 over V1 equals RPM 2. So that should kind of hopefully establish that if the prime mover was going faster or slower, but that's usually not how we control this thing, because this would just be a constant speed motor on this side or some kind of constant input, and out here you would have better control at your shunt field rheostat, no? This would be more an operator's control. So thank you for your time, and I hope that explains some of your stuff about DC self-excited shunt generators. And here is our schematic diagram in our book. Here's kind of some lab values I had for the DC shunt generator, but as from my lab, should be able to see them. So thanks for your time and have a good day.